Today I will be talking about Tutorial 3 in the VARS-TOOL package. This tutorial covers the sensitivity analysis with correlated and non-uniformly distributed inputs. For this exercise, we will be doing sensitivity analysis of the HBV-SASK model with correlated parameters. An example research question for this tutorial would be: suppose you have a hydrological model with uncertain parameters that follow a given multi-variate distribution. Which parameters are the dominant controls of model uncertainty in the estimation of design flood? For example, a 100-year flood. First, we need to import the important libraries, including G-VARS and the model class. This model class creates a wrapper around the desired model so that it can be inputted into VARS. To run a cell, you press Shift-Enter. And now we introduce the model. To do that, we define the function of interest in sensitivity analysis. Here, the following function runs the HBV-SASK model and returns a single output such as flux, or a state variable, at a certain point in time, or a signature response such as the highest simulated peak or an estimate of the 100-year flood. So I will define this function. Next, we wrap the function in our model class so that we can run it in the VARS program. Here we can run the wrapped function with an arbitrary input and check the model output just to make sure that it is working correctly. And as you see, it outputted a good number. Now we set up the G-VARS experiment. To do this, we first need to know the parameters in the G-VARS experiment. In Table 1, we can see the attributes that G-VARS inherits from VARS. I will leave it here for a few seconds so that you can pause and read what each of them do. As mentioned previously, G-VARS inherits the attributes of VARS explained in Table 1, but it modifies parameters and adds 3 new attributes called core-mat, fictive mat flag, and numDir samples. Parameters in G-VARS includes the name of every model parameter, the distribution it follows, and the parameters specifying that distribution. The distribution currently available and their parameters are listed in Table 2. I will pause for a few seconds so that you can pause the video and read what each of the parameter distributions are that are supported. Now we'll talk about the new variables that are added to G-VARS. There's the core-mat, which is the correlation matrix, which includes the Pearson correlation between every pair of parameters and must be defined as a NumPy array. There's fictive mat flag, which is a true or false value to turn on or off the estimation process of the fictive matrix. This flag essentially needs to be on, but if this estimation becomes cumbersome in high-dimensional problems, the user can turn it off. In that case, G-VARS assumes that the fictive matrix is identical to their original correlation matrix. This assumption may be generally acceptable in complex and high-dimensional problems, but is not recommended for lower-dimension problems. NumDir samples is the number of samples G-VARS takes along each direction for every star center. The use of inputs with custom distributions will be explained in the next exercise. There is also a small tidbit for advanced users. I will leave this for you to read on your own time. Now, to define the G-VARS experiment, we need to define a couple variables. The first one being the parameters. We set it up in a dictionary here, with the key being the name of the parameter and the values being the distribution parameters mentioned previously, along with the distribution type. There's also the correlation matrix, which needs to be set up in a NumPy array. Everything else can be seen here and can be set up accordingly to what you desire. Now I will run the experiment. Now that the experiment is done running, we can see that all the loading bars are complete. Now we can check out the results of the G-VARS analysis. The first one we will look at is I-VARS, which stands for Integrated Variogram across a range of scales. These indices are the primary sensitivity indices by the VARS approach. First, we will print them. Next, we are going to look at some plots of the I-VARS indices. We'll be looking at specifically the I-VARS 50 indice called the total variogram effect. This is the most comprehensive sensitivity index. We will also be plotting sensitivity results on the log scale to help us better differentiate less influential parameters. So first, looking at the regular plot, we can see that FRAC, alpha, PM, and FC are probably the most influential parameters. And when we look at the log scale, we can help better differentiate the less ones and see that C0 is more influential than TT and ETF, and so on. The next result that we can look at is the Syllable total order effect. Here I will print the results. And now we will look at some plots again. Here we can see similar results, but now this shows that PM is much more influential than the rest of the parameters. On the log scale, though, we can see that there's more influential parameters than just PM. In addition to IVARS and Syllable indices, VARS estimates various versions of Morse derivative-based elementary effects as side products, mainly the mean absolute elementary effect and the mean actual elementary effect. It might be noted that in the derivative-based approach, the user needs to choose a delta step size. For numerical estimation, it is an important point to make that in the derivative-based approach, the user needs to choose a delta for numerical estimation of derivatives. It is recommended to go with the smallest delta available here, which is equal to delta H, but the user could also choose any integer product of delta H as well. Now we will look at some plots of these results. Here you can see that in the mean absolute elementary effect and the mean actual elementary effect, the results are a little different than the previous graphs we've seen. This is because it is a different approach. It is important to note all the different approaches in the VARS-TOOL package so that you can have a better understanding of the sensitivity analysis as a whole. For advanced users of VARS, the directional variogram may provide a wealth of information about the structure of the model response surface, so this is what we are going to be looking at next. A point to make is that variograms are most meaningful when H, the perturbation scale, is between 0 and 0.5 of the parameter ranges, but the user can investigate the entire perturbation range if they want. Here we can look at some of the values that were printed. Note that some of the values in the variogram will be none when using G-VARS. This is because the sampling method is completely random, and then we use binning to create the H values. Sometimes we will not always have H values for every parameter. Now we can look at some of the plots of the variograms. Here, this helps you determine the sensitivity of the different parameters by looking at how they increase as the perturbation scale increases. Here we can see that PM, alpha, and FRAC increase as the perturbation increases, while the rest don't increase as much. On the log scale, you can see something similar, but it's more differentiating between the lower sensitive parameters. There is a delve deeper section for more advanced users, but I'm going to leave that for the user to read themselves. Thank you for watching the video, and this was tutorial 3 for the VARS-TOOL package.